So good evening to all. Welcome to 12th week and the final week discussion on the electrical machines 2 course. So in the last week discussion, we have uh, last week means in the extra session we have solved some problems, and before that week in the week 11 we have started the concepts of synchronous machines. We discussed the equivalent circuit of synchronous machine and derivations of some voltage EMF induced equations. So, in our final session today, the 12th week of discussion, we will be extending the discussion on the synchronous machine. But I would say this week discussion will be very important with respect to competitive exams like GATE and all. Because in the GATE, if you see every year, direct questions will be asked on this particular topic which we are going to discuss today. This is based on the excitation of the synchronous machines and how it behaves in the how the effect of variation of excitation on the motor is a very important and very easy concept if you understand correctly. But I would say every year at least one question will definitely be there on this particular topic. So I would request everyone to be attentive and participate in the discussion along with me so that you will understand the concept as much as possible. So yeah, let's start with that intro. So today we'll be actually discussing about the effect of variation of excitation of synchronous machine. Okay, so excitation, what exactly is an excitation in a synchronous machine? In the last week, the 11th week discussion, we have discussed that inside like to make the synchronous machine work, it needs a doubly excited machine where our rotor is also being excited by a field excitation, DC field current. So that's exactly what excitation we are talking about. So that is the excitation, nothing but the DC field current excitation. Now we will discussing all the concepts in it. But before we start, we let's have a quick assumptions which we will be making to make it analysis a bit more easier. So inside in equivalent circuit of synchronous machine, as last week we saw, there is a series resistance and a reactance either side of excitation voltage as well as the bus voltage, which is V. But for the simplification purposes, we are neglecting the armature resistance RA and assuming it to be a zero because for it just makes easier to understand the concept. The concepts remain same, but just for the simplification purpose, we are assuming RA. Let me just write here. R is equal to 0. So first we will do for generator mode and then later we will go for the motor mode. So let me just draw how a basic synchronous machine would look like so that we will see where exactly the excitation is going to the machine. Remember the stator, three-phase winding would be there on the stator. So we know this, and here we will have rotor, right? So usually this stator is what which is connected to the bus. Let's say this is the bus side. Okay, if three-phase bus. Now I'm connecting this here. Okay, now my stator is connected to my bus, and this particular rotor winding here, I am making field current flow through it, where I will provide my excitation. So here it is a this one field winding. Okay, I connected now my machine to the bus. Since we are discussing the generator mode now, what is a generator? In the generator, there should be some push to the rotor. Like let's say the rotor is being driven by a prime mover. Usually, what are prime movers? What what is a prime mover in real world would look like? Any idea?
It's a mechanical which is revolving, sir.
Right. So it's a mechanical movement we are giving to the rotor. Usually, prime movers could be steam engines, water turbines, steam turbines, and also diesel engines. So etc. So which can give a mechanical rotation to the rotor. So when we couple these mechanical systems to a rotor, we are externally making our rotor to rotate. So this will generator will rotate, and it will generate some voltage, and it will feed power to the bus. So we are giving power to the bus because it's a generator. If it's a motor, it will take power from the grid. But now we are feeding power or current, whatever, into the bus. So if we increase the steam input from the turbine, I mean the rotor is directly feeded to the steam engine. Now I am increasing my steam input. Steam input increment means what? So whatever the real power, that is I am giving input from my mechanical side, and it is being delivered to the output side to the bus. So for a if I'm increasing the steam input, the power into the bus will also will be increased. So that's the normal. So the more the steam I'm giving to the system, the more the power will be injected into the bus. Now, let's say my given steam input is constant. I have kept my steam input always constant. Let me just write it here. For a given steam input means it's a constant steam input. My real power input from the mechanical side is constant now since I fixed the steam input. Okay, this is constant. Now output power delivered to the bus will also be constant because for the fixed input there will be a fixed output. This output power is being delivered to the bus. The both are constant. So now for a constant output real power condition, we are now analyzing our system. Okay. So in the equivalent circuit, per phase equivalent circuit, if you remember, there is a excitation voltage EF. Since we neglected the resistance, it will be reactance, and this is the bus. Now this is a bus side. Now the generator is being injecting current to the bus, and this is excess. So for a constant output real power, what is the output power equation? This is the output side. This is the input side. The output power equation, voltage, current, and the power factor. Okay. For three phase, 3 V Ia cos theta. Now, where the theta is the power factor angle, theta is the angle between V comma Ia. Okay. Now, the V, whatever we are seeing here, it's the bus voltage. You cannot change bus voltage. Bus voltage is always constant from the grid, whatever is coming from the grid. Now, from the last week discussion, we have derived also a power equation. You remember from the E is equals to V plus IA, and then substituting in the apparent power equation. Then P out, we also know with this VIA cos theta is also equals to EV by XS sin delta. Now this is constant. Okay. Now, if we recall the formula for EF, the EMF induced formula, the last week also we have talked about it. I'm writing the formula for EF here. Root 2 pi, frequency, field, winding factor, and phase. So Kw is a multiplication of distribution and pitch factor. So now this is the formula for EF. In here we are varying this field current, right? In the IF, in the rotor circuit, the IF is being changed. Now IF without changing the input or output power, since we have fixed the steam input and also we know the output is fixed now, without changing the input and output power, we are varying the excitation now, right? So since I am varying my field current IF, it is directly proportional to phi f. So phi f will vary proportionally to my field. So whatever my field current, field excitation is, so that's how my field flux would also vary. Now, since IF is proportional to phi f, as I vary my IF here, this would vary. This phi f would vary. Now, if if you observe the rest of the terms, they are constants. So if my field current is being varied, I can say that my induced EMF in the generator will change. Okay, so let's see this particular phenomenon in a phasor diagram. It will be very interesting to observe this variation in a phasor diagram. Okay, excuse me. This is V. This is a, suppose this is a bus voltage. I'm taking it as a reference. So at some excitation, let's say some IF excitation, I will have some initial armature current IA1. Okay, I'm just drawing the IA1 as a lagging power factor load. So I'm taking IA1 here. So this is clear. So V and IA1, this is the theta 1 at some condition VA1. Now delivering a lagging power factor load at this theta 1. From output power equation, we have output power is equals to 3 VIA cos phi, right? P out. But this is constant. So 3 is constant, V is constant. So this product IA cos theta must be constant. So IA cos theta has to remain constant in order to maintain a constant output power. So therefore, my output power is constant. No matter how you play with the field current, IA cos theta has to remain constant. You can vary your excitation. IA would vary, but not IA cos theta. IA can vary, but the IA cos theta should not vary, right? So in other words, what I'm saying, my IA cos theta, if you see in the phasor diagram, what is IA cos theta? So this is IA, this is theta. The projection of IA onto this V axis, this one, this this is the axis where you will have the IA1. So this product, this projection of IA onto this one, this is the IA cos theta. That product should, like, I mean, that projection should be constant. So the tip of this current phasor IA, whatever this tip is, so this should always stay on this line, right? If it stay always on this line, then only the projection onto this V will always be this length, this one particular line. So this will always be cos IA cos theta. That will always be constant. Now let me draw EF1, the excitation voltage here. What is the excitation voltage? EF1 would be equals to V plus the IA excess drop. So IA excess drop would be perpendicular to this. So if it is like this, perpendicular. So IA excess, right? So this will be JIA1 excess. So for this particular IA1, this is the IAX1 drop, and if I join these two, it will be EF1. No confusion here. EF1 is nothing but V plus the JIA axis drop that we have drawn, and the angle between EF and V would be the load angle, delta 1. I am taking it. Okay. Now, so here we are seeing EF, V, and IA1. So from the power equation, which is the other power equation, we know 3EFV by x sine delta. We also know IA cos theta is equals to 3EFV by xs sine delta, right? So again, 3 is constant, V is constant, xs is constant. So this EF sine delta product should also be constant. This EF sine delta should be constant. So again, what is EF sine delta? This is delta. This is EF. EF's projection on V would be EF cos delta, but I need EF sine delta. EF sine delta would be this one. This particular length, the perpendicular length from V, this is the EF sine delta projection onto the perpendicular of the V. So this is the axis. So the tip of EF here, this particular tip here, it should always lie on this particular line, so that EF sine delta would always be constant. So these two are my constraints. I should keep IA always on this particular axis, and EF should always be on this particular line, locus, so that my EF sine delta as well as my IA cos delta would be constant, which is the vertical line EF sine delta, that it should be constant. Now we increase the field current. Let's see what happens. So before that, what are the previous all operating points? Case 1. I have certain excitation. I have IA1, theta 1, delta 1, EF1, and V. V anyhow it's constant bus voltage. Now what I do, I have increased the excitation. IF I increased. So from the equation we have shown, if I increase IF, EF would increase. Both will change. So my output power should remain constant anyhow. So my tip of EF1 phasor must always lie in this particular line. So what happens to my EF since I have increased my EF, let me just write the equation of EF, EF2 now. V plus J IA2 excess. So IA has increased to IA2 now because of the excitation increment. Now let's first draw the JIA2 excess so that I can know where exactly my IA should be there and EF should be there. I know EF should lie on that point, IA should lie on that point. Let's first draw IA2 excess. Now IA2 excess plus V should give the EF2. But I know EF2 will always lie on this particular axis. So I am right increased IA2 excess. So if I join, because the tip of this particular should remain here, then only I can have the EF join this one. This is EF2 and this is my new load angle delta 2. Since I know my JIA axis to drop here, and then now we can fix where is my IA2, because IA2 will always be perpendicular to my IA2 axis drop, right? So I'll project this particular onto this locus. This is my IA2 axis. So IA2 axis would be always in perpendicular to my IA. So now I can fix, I know already where IA should be in this particular thing. Okay. So even if you have a from this here, this will be here and this will be perpendicular and this will be my IA2. Or else you can just draw from this point, you can draw perpendicular to the projection of JIA2. It will come at this particular intersection point only. So the tip of IA2 must lie on that line. If IF increases, my IA2 increased and IA2 axis drop will increase, and then my EF2 resultant I have seen now. So we are coming from the back side because I know first my EF has increased. For that EF, what would be my IA axis drop I have calculated, and the projection should be the IA1, IA2. So now I have got all the equation. Now this is my power factor angle theta 2, right? So now my new operating points, case 2, IA2, theta 2, delta 2, EF2, and B. V anyhow would remain constant. Now let's see one more interesting case where we will reduce our field current. That is, I have reduced the IF and I have reduced the EF. So since I reduce my excitation, what will happen? My EF will reduce, excitation voltage will reduce. So, but I know what is my EF sine delta vertical length. It will always be in this. So EF1 is initially this one. EF2 is after increment. Now, if I reduce EF1 from this, I will have, let's say, at this point maybe, or else at this point I have reduced till this bit. So this is my EF sine delta, again constant. Now I am drawing my this point IA axis drop. This is my J IA1 IA3, sorry, IA3 axis. This is my EF3 IA3 IA3. So now can you draw the IA3, because this is now it's in here. If you project this perpendicularly onto the axis, this is the axis I know, right? So I need to project this one onto this one. Okay, maybe I can just draw like this. So for that it will be easily visible. maybe here. This is JIA access. This one JIA3 access. So I just wanted to as bend because I wanted to do a projection here. That's why I draw it like that. Okay. So I'm just joining the EA. This is EF3 because of the reduction in the excitation and the projection onto this one because I know always my tip of IA should lie here. So I will join this now. This is IA3, this is EF3, and this is JIA3X3, and this is delta now, delta 3. And theta 3 is this one. Right? No confusion in this. This is very straightforward. You just have to make sure where my EF sine delta and IA cos theta should line. The locus once you got it. So it's clear now. So this is where my operating points would lie. Now for case 3, I have reduced it. My operating points are IA3, theta 3, delta 3, EF3, and B. So now, if you observe the diagram once, it's this phasor diagram. For the case 1, IA1, the power factor is lagging. When I increased my excitation, the power factor still remains lagging. But when I decreased my excitation, you have seen the IA has shifted to top and my power factor became leading here. Also, we see the length of EF till this point. If you see till this point, after, above this line, all the EF excitation voltage E, the lengths of EF, this particular total lengths are more than the length of V, right? Well, this is the length of V, but if you see after this point, all the excitation voltage lengths are greater than V. But in the when I reduce the excitation, EF3 became here. Now the length of EF3 is less than my V here. So my excitation is less here, indicating that my machine is now under excited operation. So therefore, for a synchronous generator, if you can able to under excite it, if you provide that generator an under excited operation, your power factor can become leading power factor. So previously we are over exciting it and my power factor became lagging. So you now understand, right? So you can vary the operating power factor of a synchronous generator by controlling the excitation of the generator. That's what my point I have to put here. So since by just varying the rotor field current, you are able to control the power factor of the generator. Now, what is an ideal power factor? So, what power factor everyone desires for? It's a unity power factor. So it's ideal. 1 cos phi is equals to 1. So can I also make my generator work at that point, because now I can control my power factor of the generator. So definitely, so we can find such excitation, such field current which we can give to the rotor, such that my generator will deliver same amount of power, constant power. Power is constant everywhere, but at the unity power factor. So that's an important point here. So we can find such excitation such that generator will deliver same amount of power at UPF, which is unity power factor. So, what can we do to make it a unity power factor? If you go back to the this particular phasor diagram, here you will see the IA axis drop is what making the IA shift to above or below, because IA axis should always be perpendicular to it. Now, unity power factor means what? Voltage and current. So this is voltage and this is current. Let's say this is current. Both are in same phase. So then this is UPF condition. If it is IA is here, it will be lagging, and IA is here, it will be leading. So I want my IA to lie on this particular axis, same as B. So if I want my IA to be here, and I also know the tip is here, so this could be my IA at UPF condition. So in order to stay my IA here, the perpendicular should be my IA axis drop. So perpendicular should be in this axis. I mean exactly here. This is my JIA axis drop. IA axis. Let's say this is 4. This is IA4. And this is IA3 axis. So my IA axis 4 is exactly perpendicular to my voltage V, bus voltage axis. And this is perpendicular to my IA4. And you see my excitation voltage here, EF4, at unity power factor. Now we can draw a curve showing how we are observing the different armature currents while I'm changing the excitation. So excitation voltage means it's nothing but I'm varying the field current IF. So for different variations of my excitation, how my armature current is varying here, you can see clearly. So this is IA4, which is unity power factor. The bottom IA1 and IA2 are having a lagging power factor, and IA3 here is having a leading power factor. So for variations in excitation IF, I can see the variations in the armature current. So this is what exactly the curve, famous V curves of a synchronous generator explain. So this is very simple. So that's how we arrive at the curves of the synchronous generator, where we can see the observation between armature current and the field current. So this is a very important question. What is the between which quantities you will have the V curve of a synchronous? V curve is nothing but between IA and IF. We will see why it is called a V curve also. So, but we have understood. So, for initially when your motor is under excited, see this particular diagram. If you remember this phasor diagram, every question will have the answer in it. So, under excited means this particular case under excited. So, this particular condition is over excited, right? So, for the under excited condition, my EF is less than V. It means under excited. For EF3, where is my IA3? Here. It is having a leading power factor. So under excited causes leading power factor and over excited causes lagging power factor. So there exists such a excitation, this is V, where we will have a unity power factor. So now you can also see the lengths of IA, armature current magnitudes. So let's say I have started from under excited. Here my IA3 is. So I'm slowly increasing my excitation. So it will IA will have this locus. So maybe here it will have, then it will have here excitation. So it will slowly reach this point IF. So my length of IA is reducing. It will reduce. Till this point it will reduce. It will be the minimum length IA in this locus. That is at the unity power factor. Now if you increase excitation further, the IA would increase. It come here, come here. So IA would increase slowly, 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 and it will go into the lagging region. So that's what exactly we are going to draw here. Now this is my ex excitation field current, and this is my IA. I am dividing this entire region into two regions. This is under excited, this is over excited. So from left to right, you will see the IF is increasing. So under excited to over excited, excitation is increasing. Now under excited, this is IA. So at very low under excitation, if you see this IA3 is having here. At very low under excitation, IA3 is having a very big length. So as I increase my excitation, the IA3 length would decrease, decrease, decrease till the point of a unity power factor. So I start from here. I'm increasing my excitation, it's decreasing, decreasing, decreasing. At this point, this is my unity power factor region where I have reached my IA minimum length. If you till this point, my power factor is what? Leading, right? At this point, you will have a unity power factor. If you increase the excitation further, your IA would increase and it will go into the lagging power factor. So like this, it will increase. So it will increase. This is the lagging power factor. This is UPF. This is lead power factor. This is lag power factor. This is under excited. This is over excited. All these you can see it in here in the phasor diagram. So that's what we have summarized the phasor diagram in the graph between IA and IF, which we are calling it as a V curve. Now, see, all the phenomenon, IA lengths, IA variation in the lengths of IA, and also variation in the power factors of the system, everything we have summarized it in the V curve here. Now, the minimum current IA, it will be drawn from the motor when my machine is operating at a unity power factor. So if you increase the field current from there, your IA would increase, your machine will go into overexcited and it will go into the lagging power factor region. So if you decrease the field current from unity power factor position, your IA would still increase, armature current would increase, but underexcited will take your motor into a leading power factor region. So I hope there is no doubt in this straightforward V curve. If you have any doubt, you can ask. So I will just write quick summary points of this synchronous generator. It's just a repetition of the V curve, but it's like you can note it down. It will be important as a taking as a note for it. Overexcited, lagging power factor, underexcited, leading power factor. So this entire whatever V curve we have seen, this is for a constant power. Let's say I want X kilowatts of constant power. I have fixed it. So for that I have got this V curve. So next I will fix for Y kilowatt for different output power. Now if at some constant power I have got this one. So if I fix some other constant power, my curve will shift, right? If you draw the same V curve for my other constant power, you will have some other excitation, some other armature currents, some other locuses of EF sine delta and IA cos theta. So it will be like this. Maybe your curve will shift like that. For some other power equation, constant power, your curve might like go like this. This is how your curve will behave. Now, if you draw all the minimum points of armature current, those are all the unity power factor. So this is the power curve P1, let's say for X kilowatts, and this is my P2, and this is my P3. And as I join all the unity power factor points, locus of uh, Mr. Jayendra Kumar, can you mute your audio? Hello, Jayendra, can you mute your audio? So, slight disturbance. Okay. So, yeah, this is the locus of all the lower IA points that will give my is just the locus would give okay whatever might be my constant power requirement, that locus is where my unity power factor operation would exist. So sorry, I have to mark the this is the IF, this is the IA, and it will be for different output power requirements P1, P2, P3, and this line locus of unity power factor points. Okay, now this is the summary of the generator. If you want to operate your generator in leading power factor or lagging power factor, now you know what kind of excitation you have to give. And if you want to operate your generator as a unity power factor operation, now also you know how much excitation you need to give. So now let's see the same analysis for a motor operation. We have started this discussion by saying it for a generator mode. See, this is a generator mode we have done. If you look into the same analysis in a motor mode, it will be same interesting discussion. We will see how the operating points of a motor and their power factors will change if we go for a synchronous motor operation. Similar analysis, but it's interesting to see the phasor diagram. Now, see, similar thing. Let's draw the equivalent circuit first, and we will see the EMF equation, and then we will vary whatever excitation we could vary. But remember one thing, since it's a motor, your machine is drawing some load here. So there is no prime mover concept here. There will be a load. Motor needs to drive a load. So if I draw the this is the grid side, bus side, V. This is always fixed. Now since it's a motor, it will draw current from the grid. This will be the excitation voltage V here, and it will rotate my motor. My motor will rotate, and it will whatever load that is connected to my motor, it will deliver to the load. So the load will also have the power delivered to it. Now, what is the equation, voltage equation for it? So again, V is the right. So my EMF equation would be whatever eliminating the IA excess drop, I will get the VF. So we will now see the effect of variation of excitation on my synchronous motor operation. So what we will do, we will vary the field current of this particular rotor machine, and then we will see the how the operating points are shifted. Again, my Ia cos theta should be my power equations remain same. Right. Let me just take a fresh sheet. So 3 VIA cos theta and IA input is constant. My VIA cos theta and my output should also be constant. VEF by XS sine delta. Those conditions remain constant. So here EF sine delta and IA cos theta will also remains constant. So if my EF would be 3 uh, since my input is constant here, I will have my power delivered to the output will also be constant. So yeah, since my input is constant, my IA cos theta is constant, and EF sin delta should also be remain constant. Those two conditions will always remain same. So let's draw a phasor diagram for the same. So this is my V axis. I will always take capital V as a reference because it's the bus voltage and it's easy to analyze from that particular point. So this is V, and EF is now V minus JIAXS. So let's say I am drawing delivering let's say IA. This is IA1. This is theta 1. It is a lagging power factor. Now IA1. Now I can get the IA excess drop, which will be perpendicular to it. This is IA excess perpendicular. But I have to subtract this minus JIA excess from it to have the excitation voltage. So it will be like this, minus JIA excess, IA1 excess. So this would be my EF1, right? So again, these are the operating points in my first case where will be IA1, theta 1, and this is delta 1 will be operating points. Now, the IA cos theta should be constant. So this particular locus should be constant because that is the projection of IA onto it. And EF sine delta should be constant. So this should be constant. This is the cos theta, EF sine delta. These are constants. So we have both the locuses, and yeah, you can we will vary the field current. So whatever it is, the operating points, what we got here, case one, IA1, theta 1, delta 1, EF1, and V. So yeah, the same thing. Now, if we increase the field current, my EF would increase. I'm increasing my excitation. My EF would increase, and my JIA access would increase, and then I can draw my IA in the similar way, and then I can see what is the power factor of it. So I have increased my EF. Now my EF2 would be somewhere here because I have increased it. So it is my EF here, and then it is minus J IA 2 axis. So this is my EF2. So just draw the perpendicular this onto this particular axis. Okay. Assume this is the perpendicular. I have not got the exact perpendicular. So this is the perpendicular. Now IA join this. You would get this particular. This is the IA. This is the second IA2. IA2 we got minus J XS2, and this is EF2, and this is my theta 2, and this EF2 and this one will have the delta 2. So my case 2 IA2 theta 2 delta 2 EF2 and B. So again, yeah, I'm just taking only two cases here. I think you have got the point what I'm trying to showcase here. Now for the motor case, we have seen IA cos theta and IA sin theta being constant, held constant. We can see the two different power factor regions based on the excitation which we have provided to the motor here. So if I increased my excitation or decreased my excitation, I can vary the power factors of it. Now, can you tell me the power factor in the under-excited condition here? So, under-excited would be my EF1 case. EF1 case, this will be the under-excited. This will be my over-excited condition. And there exists that point, it will be the unity power factor. Same thing. This is the IA IA3 excess drop, so that I will have this EF3 at unity power factor. So for this will be my IA3. So same thing, IA3 would be the minimum length, and above that and below that you can just increase the armature current. Now tell me the power factor in the under excited, that is EF1. EF1 is IA1. IA1 have a lagging power factor, and over excited is IA2 because it's EF2. EF2 has a leading power factor, and your UPF has a unity power factor. So same thing, we can draw a similar kind of curve for the synchronous motor as well. Just drawing here. X-axis is excitation, y-axis is armature current. So there, dividing my space into two conditions, that is under excited and over excited. From left to right, my excitation will increase, and from the under excited, if you see, this is one lagging condition. IA would start from a peak point, and it will, as you increase the excitation, your IA would reduce. Start from here. IA would reduce as you increase the excitation. It will reach a point, unity power factor, and then you further increase the excitation, your IA would increase, but the power factor would change. So this is the unity power factor. So under excited having what power factor here? Lagging. So this particular region will have a leading power factor. Same thing for different power, you will have a this kind of curve. So your curve will be shifted to the rightwards. It won't be following the same. The unity power factor won't be occurring at the same field current. So your field currents required for unity power factor would change, as well as the IA. So that's why your curve is shifting to different uh, towards the right. Anyway, let's have a quick summary of the synchronous motor operation, just the same way we have looked for the generator. You can operate your motor in the over excited, as well as you can operate your motor in the under excited. Over excited will give you leading power factor. Under excited will give you the lagging power factor. So if you see the same for generator, it's a reverse operation. Under excited is giving a leading here, where over excited is giving a lagging power factor operation. Right. So this is the basic understanding of the synchronous motor, effect of variation of excitation on the synchronous motor. So one application of this particular thing in the actual power systems is the condenser. So this is a very nice property that our synchronous motors have. These are important points which I'm going to say now. So please listen carefully, like how exactly we are applying it in the real world. Because this property of synchronous motor, we can use it. So we can use this particular motor and we can draw leading power factor current, because leading power factors is always what is important, because as power factor is your lagging, your it's not desired to have a lagging power factor. So previously, in the overexcited synchronous motor, it was considered to be the other meaning of a overexcited synchronous motor is something but a capacitor. Because see, your overexcited synchronous motor, it's always giving a leading power factor. So when what is the condition of capacitor? Capacitors also always draws leading power factors, right? Inductor always draws a lagging power factor. Now, if you connect this particular synchronous motor and operate it in overexcited condition, it will always draw leading current, whatever load you have. Whatever your load power factor could be, it can improve your load power factor by drawing the leading power factor current, right? So let's say you have a big factory, maybe a very big factory with all the motors and machines running all over. Now, usually, what motors you have in a big industry or factory? Induction machines, because of their rugged construction and low maintenance and good operating power factor, this 0.8, 0.7, whatever it is. So you will have a induction machines all over your factory. So induction machine loads are usually lagging. Induction motors always provide for a lagging power factor. Now there is a big factory you are having, and you always know it's better to operate your power factor close to unity power factor. So what people will do, there some supply it is being provided by the government, and there is this factory which is you are having in the your place. So let's say this is your factory. So this is my garment supply. So you are taking supply from the garment. So this is government side, and this is your side, consumer side. Factory, you have a factory now. Now, whatever current you are drawing from the government, it will be definitely lagging, because you need to supply all the lagging loads here, all full of induction machines and lagging loads, right? Now your voltage is here, your current is here, and your theta is always lagging and poor power factor. Okay, let's say it's like that. Now, if your power factor is low, because government knows whoever is taking my current, they has to pay to the government. But whoever is taking the lagging power, because lagging power factor is not at all suggested, and it will deteriorate the conditions of the motor, and it's not good for the operating power factor. The efficiency would be low. So what government will do? Government will charge that particular factory very heavily. So it sees that, okay, this particular factory is drawing a lot of lagging current from me, so I will penalize them. I will impose more charges on them. So what people will usually do is they will connect a capacitor bank, where just after the supply and before the factory, between these two bodies, they will connect a capacitor bank. So let me just take a empty sheet. So initially there is a factory here. It is taking supply from the government and it is all the lagging. Now what I will do to avoid penalizing and heavy charges, there is this my factory. So this V and this is IA now. So this is the power factor theta 1. It's a poor power factor, lagging also. So now the second case, there is a factory and this is the government. I have connected a capacitor bank here, right? So anyhow, this will take lagging only, but this will take leading currents capacitor. So whatever current that is being drawn from the government will not be that much lagging. So let's say this is my voltage and this is the current drawn by my lagging IA. So this same current. The load is same now, but your capacitor is drawing some leading current here. IC. It is exactly 90 degrees to the voltage, right? Now the resultant current should be this one that is being drawn from the government. So the improved power factor is theta 2 now, better power factor. So this is what every industry would do, like having a capacitor bank and improving the power factor. That's fine. That's how it should be. Now your factory will take the lagging current, whatever, and the load is there, but the total current drawn from the supply would be now IA lagging plus this IAC in phasor form. IA, it's not algebraic sum, IAC is equals to I resultant. So see, the resultant will be now overall power factor of the factory is now improved. So earlier, what people used to do is to connect capacitor. Okay, for this particular factory load, I can say I have to connect this value of capacitor. So what if your load requirement changes? Maybe the factory needs to supply not 1 megawatt, maybe 2 megawatts or 1.5 megawatts. Now, whenever your load keep on changing, the capacitor needed to attain that particular power factor will also change. So every time you need to connect and disconnect the capacitor bank based on the load requirement. So people are finding it very difficult because every time removing connecting the capacitor to the bus system is not a that much suggestible and also not a easy process. Now what people are doing now, they are instead of connecting this capacitor, they are connecting a synchronous motor, right? So this is factory, and between this they are connecting a synchronous motor here. So whenever you connect a synchronous motor, we have seen the principle of synchronous motor. What is this? This is the synchronous motor and this condition overexcited, and it will always draw the leading power factor. So whenever you connect a synchronous motor and adjust its field current such that it always draw leading power factor current. So whenever your load changes, you just have to change the excitation now. You don't have to replace any capacity. It makes your process very easy. So just remove my capacitor bank altogether, connect a synchronous motor, and operate it in overexcited condition. And always operate your synchronous motor in the overexcited so that it will always draw a leading power factor. So based on the load changes also, your synchronous motor is adaptable to it. You just have to go for another excitation. So from the curve, if you see, so this is my IF and this is my IA. So for a motor, this is the overexcited and this is a leading power factor. Let's say for output power requirement, this is the current it is drawing. maybe for different requirement of load, maybe you can still go to the IA here different IAs you can draw, still remain in the overexcited condition, still drawing the leading power factor. So that's possible. And you connected a synchronous generator and it will draw some leading, it will go from lagging, and the total current drawn from the government would be always a leading, I mean, improved power factor current. So this mechanism, or you can say this particular device, whenever a synchronous motor, I will write it here, it's an important point. When a synchronous motor is used to supply a leading current, right? It is called as synchronous condenser. This is a most commonly used term in the power systems. So, employ a synchronous condenser and it will improve the power factor of the system. How it will improve? That's what we have seen now. This is the application of a synchronous motor. So, whenever you hear the word synchronous condenser, the thing which you have to come in your mind is, okay, this is not a synchronous condenser, it's a
Sir,
synchronous motor operating in a overexcited condition. Yeah,
we generally use capacitor na, for the substation
yeah,
to
yeah,
improve the power factor.
yeah. Because substation
Suppose
knows
one
what
minute,
the load is.
the synchronous condition we use,
Huh.
then it in overexcited case is a leading power factor for
Yeah,
motor. So, but it will draw itself some current from the field, na,
yeah. It will
leading
draw.
yeah. So
You can.
this how it is beneficial in comparison to capacitor.
It's beneficial only if you have a varying load requirement. See, whenever
Cost
you
wise, cost wise, suppose
cost wise,
if
it's
you
not.
use
It's not. See, the purpose of synchronous condenser is it will supply both to a mechanical load as well as provide a leading current. So that's where it will be advantage. You can draw a mechanical load also if you have a synchronous condenser. If there exists such kind of requirement, it will supply to both mechanical load and also provide leading current to the factory by drawing the leading supply from the government. That's it. Usually in the factories we see there is no synchronous condenser because there is no requirement of drawing any mechanical load, and also your capacitor knows whatever load requirement is at the substation. You know, this is what I have to deliver. The fixed capacitor bank will be there and they will use it. But I'm just saying, in case of varying load requirement, you need to replace your capacitance. Continuous replacement of capacitance might not be advisable. So in that case, it's suggestible to go to a synchronous condenser where you can use this synchronous condenser to supply to mechanical load as well as providing leading current. That's it. Yeah. So yeah, that's it. So let's have a look into this problem. It will cover all the aspects we have studied today and also last week from the equivalent circuit. So you please solve it with me. It's a very a nice question. We were given a lot of data and we were asked to find three different parameters. So let's read the question, read along with me, and take a pen and paper. So a round rotor star connected synchronous motor has a synchronous impedance of 0.2 plus J2 omega per phase. So ZS is given 0.2 This J2 omega per phase. And for the purpose of the power factor improvement, see, there is a plant existing there. They want to improve the power factor of that particular plant. So this motor is used as a synchronous condenser under no mechanical load. Okay. So it is not it is not rotate, it is not delivering to any mechanical load, but the sole purpose of condenser they are using here is only to improve the power factor of the plant. Okay, fine. Now we know the application of the synchronous condenser here. Now it is required to draw minus 25 kVAR reactive power. So it's a negative reactive power. It is drawing from a 440 volt line to line bus. So the negative whatever sign it is used to indicate that it's used to draw the capacitor. So when it is drawing, it's leading. Drawing means it's taking itself. It's not injecting any reactive power to the bus. It's drawing, so it's a negative value. Now at a leading power factor, it has a constant losses of a 1 kilowatt. Now what is the line current? Required excitation voltage per phase. What is the voltage excitation that is required for the plant? And also the power angle delta will be uh, dash degree. Okay. Synchronous motor as a synchronous condenser, that's we have discussed well. And now synchronous condenser uh, means it's something but a synchronous motor. Now let's first write the data first and then write the equivalent circuit of a synchronous motor and everything will be clear then. Zs is equals to per phase and it's a 440 volts bus voltage line to line, and Q is given minus 25 kVAR and constant losses also given 1 kilowatt. Now it's a synchronous motor. What is the equivalent circuit of a motor would look like? There is an excitation voltage and there is a resistance also given, so we can't neglect it now. So this is the bus voltage and this is XS and this is RA and this is 2J, it is 2J and this is zero point 0.2 ohm and the EF we don't know, and yeah, this is the IA, this is V. So okay, now the equation would be V is equals to, it is drawing, there will be IA drop and adding to the EA would be total bus voltage, EF plus IA ZS. Now this, since it's what is the type of connection of the motor? So star connected synchronous motor. So since it's the star connected, I can say line current is equals to phase current since it's the star connected. Now in this particular equation, we know the IF we don't know, we are supposed to calculate, and IA is what asked first. IA, what is the line current would be? IA we need to calculate, and ZS we know. There are two unknowns. How to solve this equation? So if you look into the question, B is 440, ZS I know. There's one more thing they have given us. The information is this Q and also some constant power that is being given. So we have a P and Q information, the real power and also the reactive power being drawn. So can we get the line current from that? Because once we get the line current from there, we just have to substitute here and we get the excitation. So what how can we get the line current drawn from the supply using this power equations P and Q? So you know the apparent power, right? S is equals to 3 V phase I conjugate. This is what we need to calculate now, right? So in order to calculate I phase, maybe conjugate, it is S divided by 3 into V phase is nothing but V line to line by root 3. right? Now, what is S here? P plus JQ. P plus JQ, we have now 1. P is nothing but the constant power, whatever it is being required. JQ, Q is having minus, so I have right minus 25. So 1 minus J25, both are kilo, multiplied by 10 cube divided by 3 into line to line voltage is 440 divided by root 3. Can you calculate it for me in terms of polar and tell me what is the magnitude and also the angle? This will be the phase current. Okay, so the answer should be around conjugate. I'm talking about conjugate 32.83 at an angle of minus 87.7 degree. So this is the phase current conjugate Yep, you obtained. Amperes. So my I phase, which is nothing but IL, would be okay. And the first question is this one, I guess. The line current would be this much, and the second question, this is the line current, and the second question is the required excitation voltage per phase. Now, excitation voltage, we already have the formula. EF is equals to V phase minus IAZS. So this particular equation for a motor. You know now IA, you have to calculate the EF from it per phase equivalent circuit. So EF would be V phase minus I phase ZS. So V phase would be 440 by root 3 minus I phase, that is 32.83 at an angle of 87.7, multiplied by ZS. ZS is zero point 0.2 plus J2. So again you will have some dash at an angle of dash volts. So can you calculate it and let me know how much excitation voltage you need? So there is no separate calculation required for the delta, because delta is nothing but the voltage angle between V and ES, EF, that is delta. So we always take it as a reference. So whatever angle you get here, that will be the delta. So 440, this is at an angle of 0. That means 440 minus IA and ZS. You can do the simple calculation. Let me know the excitation voltage you got. Okay, so the excitation voltage would be 319.5 at an angle of minus 1.64 volts. So this is the magnitude of the excitation voltage, and this is nothing but the delta. Delta is equals to minus 1.64 degree. So also observe what exactly you have been asked in the question. So the first question is asked in the line current will be in amperes and the required excitation voltage in phase. So you can just write the amplitude of amperes here and the amplitude of the voltage here, and the power angle delta, we just have to enter the positive number in degree. So you just have to write the 1.64. That should be the solution for it. Okay, here Since it is not driving any load, whatever active power it will take would be equal to the constant losses. That's what it was given in the question, 1 kilowatt. And reactive power, it is definitely, it will try to take some reactive power minus 25 kilowatt hour. It's just additional data. The more the data they give in the question, the easier the question would be. So always make sure you have utilized all the data. So if you couldn't move forward in any numerical, let's see what data they have given, and maybe you can make use of it. So yeah, I hope you understood the problem. It's a simple condenser based problem. So now, if you, the bottom line is, if you can provide this much excitation, that is 319.5 volt excitation at that particular delta, your synchronous condenser would improve the power factor of the plant. That's the ultimate motive of the numerical here. Okay, now let's have a quick look back at the today's discussion. So today's discussion, we started on the synchronous machines concepts only. In the synchronous machines concepts, we started with discussing the effect of variation of excitation on the machine. We first discussed the generator mode and then discussed the motor mode. So the main motive of today's discussion is, by controlling the excitation of the my rotor, by controlling the DC current flowing through the rotor, I can make my synchronous machine operate as leading power factor delivering machine or lagging power factor delivering machine, and that's very useful with respect to the practical application of any industry or any power requirement based station. So we have seen a detailed for a constant power load requirement. We see the detailed phasor diagrams based on two different conditions having two IA cos theta and DF sin delta, that makes the output power constant. So basing on those two conditions, we have drawn these different phasor diagrams. So they might look complex, but I hope you have got a clear picture of it, how easy they are. And by looking at the phasor diagram, we can see how by variation in the excitations, we can get the different operating power factors of the machine, how unity power factor can be got, how leading and lagging, how the under excitation and over excitation will change the power factors of the synchronous generator. And then we have seen the famous V curves of a synchronous machine. For a generator and motor, there are different V curves, because the curve remains same, the axis remains same, but the operating regions would definitely remains different. So leading and lagging will be interchanged for under-excited and over-excited in case of motor and generator. And then we have a summary of it for different power requirements. The curve shifts towards top and right, giving the locus of different unity power factor currents. And then we replicate the same discussion to a synchronous motor operation. Based on the equivalent circuit, we got the voltage equation, and based on that, we have drawn the phasor diagram replicating the multiple operating points and as well as the operating power factor regions, how the under-excitation and over-excitation will give us different power factor operations. So, and then we have discussed the practical application of the synchronous condenser. So, how a factory drawing lagging currents from the government can reduce their charges from the government by introducing a synchronous condenser, and how it can be beneficial over capacitor when there is a diverse load requirement at your end. So that we have solved. And yeah, then we have seen a problem based on that application of synchronous condenser, where we were asked to find out the excitation required to in order to improve the power factor of the total plant. So yeah, we solved it, and that's it. That's it for today. And yeah, I would suggest you to go through the total 12 weeks summary sessions we have discussed, and notes also uploaded in the portal, and videos are there, and also refer to the lectures delivered by the professor to have if you have any doubt in any concepts or anything. So yeah, I would wish you all the best for the examinations as well as any future competitive exams you will be taking for this course. Be thorough with the concept, and strong at fundamentals. Don't go for any complex things to remember. Just be strong in the basics fundamental laws of any electrical engineering, like Fleming's left hand rule, right hand rule, what is the Lenz's law, and right hand thumb rule, and that actually defines entire machines. So how machine rotates, how the motor rotates, everything is depends on the basic rules only. So I would suggest be confident in the basics, and the results would follow. So yeah, thank you for having the very good session this semester, and I look forward to taking the same course in the coming batch or anytime I would get the opportunity. So if meanwhile, if you have any kind of doubts, you please don't hesitate to raise in the discussion forums, as well as any comments, or in the any comment section of the recordings or videos. We will definitely try to get back to you. And on this note, I will sign off from this electrical machines 2 course. And
Yeah, thanks a lot, sir.
yeah,
And
thank you.
I want to ask one thing.
Yes, Dinesh.
They were showing some NPTEL documents
Okay.
while the week one, week two, week three, na?
Huh.
So sometimes they were showing NPL documents. They were explaining all the theory behind the problems.
Okay.
Is that available?
I don't know who is explaining for this particular course. You are being
Yeah,
provided.
yeah. I saw in Kaushik Ghosh, sir.
Okay.
Whenever he was starting the problem, na, he
Hmm.
was opening some doc or PDF file.
Okay.
Then he was going through that. In some problem, he directly went there and he was explaining this like that.
What is it? What is that PDF document have?
It's written like in I think it's some NPTL mark and that.
So you mean the solution of a problem?
No, no, not solution.
Huh?
Solution is already given.
Okay.
It is uploaded, I think.
Okay. Then what's the
It
document?
is some theory behind the theory, the exact theory behind what are the problems.
I think we were not provided any kind of such. Maybe he made the document himself, I guess.
Okay,
Yeah. Okay.
okay.
Okay, Dinesh. Thank you, and I wish you all the best. You are being consistent in all the weeks and actively interacting with the course. So I wish you all the best, and I wish you success in the future. Thank you. Thank you, Dinesh. Bye.